Hello and welcome to the Embedded Online Conference. My name is Miro Samek, and in this session I'm going to show you, step by step, how to design and implement an embedded application using the modern approach, with hierarchical state machines, active objects, visual modeling, and automatic code generation. I've been working with the embedded and real-time systems for almost 3 decades now, about half of that time at Quantum Leaps, the company I founded back in 2005. My main interest is in modern embedded software, and I already introduced this subject at the last year's edition of the Embedded Online Conference. My today's talk will be a continuation of that theme. I will try to make it self-contained as much as possible, but I obviously cannot explain everything from first principles. Therefore, I will be occasionally referencing my last year's talk, as well as specific lessons from my free video course on YouTube, which now has close to 40 lessons on various aspects of embedded systems programming. The approach to developing real-time embedded software I'm going to show you is recommended by experts on concurrent programming, but is not mainstream yet. Therefore, I hope you find the practical demonstration of the method both interesting and inspiring. Regarding the agenda for today, I will start with explaining what we are going to do, and then, more importantly, why we are doing this. After that, I will walk you through the main steps of design and implementation, explaining the thought process, tools, and new possibilities this approach opens. The application I chose for today is a little fly-and-shoot type game. We'll build this game for an embedded board based on ARM Cortex-M microcontroller, but most of the code will also run on a Windows PC in a pixel-exact prototype of the game. So let me just play the game in the Windows prototype and explain how it works, which will serve the dual purpose of learning how to play the game and provide a specification of the problem for the purpose of developing the software. For this I need to provide a few details, so please bear with me. The game starts in the introduction mode, where it shows an animated logo. After a few seconds, the game switches to the demo mode, in which the tunnel walls scroll horizontally and the text "Press button 0" flashes in the center of the screen. When you press button 0, the game goes into the playing mode. Here you have a little ship on the left, which keeps falling, but you can lift it by pressing PB1. You can also fire a missile by pressing PB0. The missile can destroy mines that are randomly placed in the tunnel. When the missile hits a mine, or a tunnel wall, it causes an explosion. You can have only one missile in flight at any given time. Any collision of the ship with a tunnel wall or a mine also causes an explosion and terminates the game. When this happens, the game enters the Game Over mode. Your score is shown at the bottom of the screen. You earn 30 points for surviving each second, and also 30 or 45 points for destroying mines of 2 types. Finally, after a few seconds of the Game Over mode, the game switches back to the demo mode, and the cycle repeats. Additionally, if you don't start playing the game in several seconds, it switches to the screensaver mode. So now the objective is to design and implement the game in embedded software. But instead of following the traditional path, let's apply the modern active object design pattern with state machines to define the behavior of these active objects. I've introduced this pattern in some detail in my last year's talk, but let me quickly recount the most important elements. So in this pattern, software consists of strictly encapsulated components called active objects or actors that don't share anything and communicate only by exchanging events posted asynchronously to their event queues. An active object processes all its events in its private thread of control inside its state machine, one event at a time, without blocking. This makes an active object responsive to any new events and thus extensible. These no sharing and no blocking restrictions sound rather draconian, like trying to do the job with both our hands tied behind our back. So why are we doing this again? Well, the traditional approach with naked RTOS threads would be exactly based on sharing and blocking. I mean, no matter how you partition your problem into RTOS threads, the LCD screen, for example, would be typically shared by most components of the game. So would be the score. Then you would need to use mutual exclusion mechanisms like mutexes to protect the shared resources. Also, there would be a lot of blocking inside the RTOS threads, for example, to wait for the numerous timeouts, the button presses and the frame updates. This is because blocking is all that RTOS does, and all its mechanisms for thread synchronization and communication are based on blocking calls to the RTOS. But as I explained in my last year's talk, this sharing and blocking creates contention and requires a lot of mechanisms to avoid collisions. That's why experts on concurrency advise to avoid sharing and blocking and instead use the active object design pattern. With active objects, you are building a collision-free infrastructure. But while this picture might suggest that the infrastructure is very expensive, it turns out that in software, the active object solution can be actually smaller and more efficient than the traditional RTOS. So, how would you go about designing a software based on active objects? Well, it all starts with partitioning the overall problem. Your main goal is no sharing and minimal need for communication among components. Here, a good starting point is the object-oriented guideline to look for the nouns in the problem specification. For the fly and shoot game, this would yield candidates like ship, missile, tunnel, and mines. Please note that not all identified components need to be active objects with their own thread of execution and event queue. Some components could be passive, running inside the active objects. For example, mines could be just passive subcomponents of tunnel, which does not prevent them from having internal state machines. In fact, they most likely will have state machines to capture their life cycle from being planted in the tunnel to scrolling off the screen and sometimes exploding after being hit by the missile. But the problem of partitioning does not end with identifying the components. As soon as you have your first candidates, you should think of assigning the resources to them. This is essential for avoiding sharing the resources. Here I want to emphasize again that no sharing will not happen miraculously just because you call your components active objects. You need to elevate the share-nothing principle to your top design goal. Also, in your resource allocation, you should include all concurrent entities like interrupt service routines, some RTOS hooks, RTOS callback timers, etc., because they are all potentially subject to concurrency hazards. In your game application, for example, you might decide that the Cortex-M SysTick ISR will own the push buttons. So here is an example of resource allocation. The display will be owned by tunnel, the score by ship, and the buttons by the SysTick ISR, where the buttons will be cleanly debounced. But this is not the only way, and sometimes resource allocation might not be completely obvious. For example, I've assigned the score resource to the ship component, but you might consider other options. For instance, score could be owned by the missile or even by the mine components, because the missile will need to keep score when it destroys something, and mines need to keep score for being destroyed. But then you remember that the score needs to increase also for survival of the ship, and this increments the score most frequently. Also, only the ship knows how long it survives. So the general guideline here is to allocate the resource to the component that makes the most intense use of the resource. Other components, also interested in the resource, will then post events to the owner to do something with the resource, instead of accessing the resource directly. Which brings us to identifying events for your event-driven application. The easiest to identify are the external events, such as time tick, generated by the SysTick timer 30 times per second to smoothly animate the game. Similarly, the player ship move and player trigger events are generated by the player by pushing the buttons. A little harder to identify are the internally generated events because they depend on how you design your application. But you might anticipate that the missile, for example, will need to report back to the ship when it destroys a mine, so that ship can upgrade the score. You can call such an event destroyed mine. Finally, when thinking about events, you should consider not just the signal, like player ship move, but also the additional information that the event can also carry inside its parameters. For example, the player ship move event can have parameters x and y, which will tell the ship active objects the exact position of the ship. With those initial decisions behind you, you can get to the most constructive part of the design, where you plan the event exchanges within your application. The most helpful conceptual tool here is the sequence diagram, which shows components as boxes aligned at the top, each one having a timeline descending vertically. The horizontal arrows represent events exchanged between the entities. The narrow boxes around the timelines represent activations, meaning here run-to-completion steps in various components. A sequence diagram like that can show you only specific scenarios, so you should choose the most interesting scenarios that illustrate how the application handles the most representative situations. The time tick event is the most important event in the game. Since it is of general interest to most components, it is published periodically every 33 milliseconds and then multicast to all subscribing active objects. Upon reception of the time event, the ship object advances its position by one step and posts the event ship image to the tunnel object. Ship image event has parameters x and y, which are the coordinates of the ship on the display, as well as the bitmap number BMP to be rendered at these coordinates. The missile object is not in flight yet, so it simply ignores the time tick event this time. The tunnel object performs the heaviest lifting for the time tick event. First, tunnel redraws the entire display from the current frame buffer. This action, performed 30 times per second, provides the illusion of animation of the display. Next, the tunnel clears the frame buffer and starts filling it up again for the next time frame. The tunnel advances the tunnel walls by one step and copies the walls to the frame buffer. The tunnel also dispatches the time tick event to all its mine state machine components. Each mine advances its position by one step and posts the mine image event to the tunnel to render the appropriate mine bitmap at the position x and y in the frame buffer. Upon reception of the ship image event from the ship, the tunnel object renders the specified bitmap in the frame buffer and checks for any collisions between the ship bitmap and the tunnel walls. Tunnel also dispatches the original ship image event to all active mines. Each mine then determines whether the ship is in collision with that mine. The player trigger event is generated when the player presses button PB0. This event is also published and is subscribed by the ship and tunnel objects. Ship generates the missile fire event to the missile object. Tunnel subscribes to player trigger as well, because tunnel occasionally needs to start the game or terminate the screensaver mode based on this stimulus. Missile reacts to the missile fire event by starting to fly, whereas it sets its initial positions from the x and y event parameters delivered from the ship. This time around, the time tick event arrives while the missile is in flight. Missile posts the missile image event to the tunnel. Tunnel renders the missile bitmap in the frame buffer and dispatches the missile image event to all the mines to let the mines test for the collisions with the missile. This determination depends on the type of the mine. To make this scenario more interesting, one of the mine objects detects a hit and posts the hit mine event to the missile. The mine provides the score earned for destroying this particular mine as the parameter of this event. Missile handles the hit mine event by becoming immediately ready to launch again and lets the mine do the exploding. Because ship is responsible for scorekeeping, the missile also generates the destroyed mine event to the ship to report the score for destroying the mine. Upon reception of the destroyed mine event, the ship increments the score by the value received from the missile. The shipped object handles the player ship move event by updating its position from the event parameters. When the tunnel object handles the ship image event next time around, it detects a collision between the ship and the tunnel wall. In that case, it posts the event hit wall to the ship. The ship responds to the hit wall event by transitioning to the exploding state. Alright, so these were merely some selected scenarios from the game, but I hope that this much of explaining a sequence diagram gives you a big picture of how the application works. More importantly, you should start getting a general idea about the thought process that goes into designing an event-driven system with active objects and events. With this better understanding of how your application should work, you can now step down to the detailed design and implementation of your events, active objects, and their state machines. But as you are entering this stage, your design decisions will depend on the underlying active object implementation you choose. In my last year's presentation, I showed you how you can build a rudimentary active object framework on top of a traditional RTOS. Because it was specific to FreeRTOS, I named that little framework FreeAct and posted it on GitHub. FreeAct provided the basic facilities for events, active objects, and time events. But for today's project, FreeAct is inadequate because it lacks many important services such as thread-safe passing of mutable events with parameters, publish-subscribe event delivery, as well as hierarchical state machines. So today I will use the professional-grade, open-source QPC Real-Time Embedded Framework, RTEF, which provides all these services as well as support for visual modeling and many other features. But going back to your project, in the QP-RTEF you represent your event signals simply as enumerated constants. By a QP naming convention, all signals have the _6 suffix, and they are all offset by the QUserSig constant. Events are represented in QP as instances of the QEVT base class provided in the framework. Specifically, the QEVT class contains the sig attribute to carry the signal of the event. Event parameters are added in the process of inheritance, so for example, the object post-EVT has parameters x and y of type uint8t. Now each signal is unambiguously associated with the corresponding event class. For example, all events without parameters are associated with the QEVT base class. Events with parameters x and y with the object post-EVT. Events with parameters x, y, and BMP with the object image EVT, and so on. On a side note, if object-oriented programming in C is new to you, you can refer to the OOP segment of my YouTube video course. Here I only wanted to mention that the single inheritance between QEVT superclass and your object image EVT subclass is implemented very simply by embedding the QEVT as the first member super of the subclass. That way, any pointer to the subclass can be always safely treated as a pointer to the superclass. The memory alignment is guaranteed by the C standard. Moving on to your active objects, they will also be subclasses of a class from the QP framework, the QActive base class in case of active objects. Now, it is possible to continue this detailed design and implementation manually, and the QP framework has been originally designed for manual coding of applications. But today I promise to show you visual modeling, for which I will use the freeware modeling tool called QM. QM is an example of a modern, quote-unquote, low-ceremony modeling tool. This means that, compared to other, quote-unquote, high-ceremony modeling tools on the market today, QM is much simpler, code-centric at relatively low level. This characterization simply means that QM maps the design unambiguously and directly to C or C++ code, without intermediate layers of platform-independent models, PIMs, platform-specific models, PSMs, complex model transformations, or action languages. There is only one modeling level in QM, the platform-specific model, if you will, and all actions in state machines are entered directly in C or C++. By the way, the QP frameworks, the QM modeling tool, and the QTools collection of other complementary host-based tools are all available for download from the Quantum Leap's website, as the QP bundle available for Windows, Linux, and Mac OS hosts. To continue with the fly-and-shoot game example, I will just open the QM model of the game, which is provided in the QPC example directory. I will then walk you through the most interesting parts of the design captured in that model. Active objects are located inside the AOS package, which is like a folder, except it holds classes instead of files. I will start with the missile active object because it turns out to be the simplest. The missile AO is a subclass of QP QActive base class. Missile adds to that superclass its own attributes and operations, and also a state machine, SM. When you double-click on it, QM opens the corresponding state diagram. I briefly introduced UML state machines in my last year's presentation, but if you'd like to learn more, I also added a few more video lessons about state machines to my YouTube video course. The missile's initial transition subscribes to the periodic time tick signal published 30 times per second. It also generates the so-called signal dictionaries for the QSPI tracing instrumentation. This instrumentation is active only when tracing is enabled and is typically inactive in the release and debug build configurations. I'll briefly show you how software tracing works by the end of this presentation. But what matters now is that the initial transition points to the armed state, in which the missile waits to be fired by the ship. In particular, this armed state does not handle a time tick event, so this is the situation from your sequence diagram where missile ignored time tick. The only event handled in the armed state is missile fire. This event is posted by the ship, who provides the missile with the starting coordinates for the missile's flight in the event parameters x and y. Missile needs to copy the event parameters to its internal attributes x and y, so let me explain the general mechanism for accessing attributes and event parameters in QPC state machines. First, private attributes are accessed by means of the me pointer, which points to the current instance of the class in C and corresponds to the this pointer from C++ or the self-reference from Python. The convention of calling the instance pointer me in C allows the code to be compiled cleanly with a C++ compiler, and I've been using it at least since 2002. The convention seems to be catching on though. For example, here it is being used by another author in a book from 2011. Now the current event is provided to the state machine as a const pointer e to the generic QEVT superclass. To get to the event parameters, the pointer needs to be downcast to a specific subclass of QEVT. This downcast is performed based on the unambiguous mapping between the detected signal, which is missile fire in this case, and the specific event subclass, which is object pose event. This event downcasting is frequent, so QPC provides a special macro, QEVT-cast, for this purpose. This macro preserves the constantness of the downcast pointer, so you cannot change anything inside the event. Also, you can use the macro to precisely define the deviation from MISRA rules for this specific event pointer downcasting. The missile fire transition goes to the flying state. Here, the missile handles the time tick event by advancing its x position by one step and going into a choice point. If the guard condition for the missile being still visible in the tunnel evaluates to true, the missile needs to generate the missile image event with parameters to the tunnel. Support for mutable events with parameters is one of the most valuable features of an active object framework, so let me quickly explain how this is done in QP. So the desired event type is first allocated by the QP macro QNew. This thread save macro allocates the specified event type from a deterministic fixed size pool and assigns a given signal to the event. Then you can set the parameters of the event. And finally, you post the event to the specified active object, at which point the framework takes over the responsibility to deliver the event in a thread safe manner. The framework also knows about all uses of the event, so it will automatically recycle the event after its last use. In fact, you've already taken advantage of the automatic event recycling when you process the missile fire event with parameters in the armed state. You didn't have to do any memory management there because the QP framework took care of it. This automation is very convenient and safe. In the else branch of the choice point, the missile flies off the screen, so the state machine transitions back to the armed state, where the missile can be fired again. The next event handled in the flying state is destroy the mine, which is generated by a mine that detects a collision with the missile. In that case, missile reposts the received event E to the ship so that the ship can increment the score for destroying the mine. Please note that it is legal to post or even publish the current event again, because the QP framework keeps track of all event uses and will not prematurely recycle the event. The transition then goes back to the armed state, making the missile ready to fire again. The animation of the explosion is left in this case to the destroyed mine. The last event handled in the flying state is hit wall, sent by the tunnel when the missile hits a tunnel wall. In that case, the missile must take care of animating an explosion, so it transitions to the exploding state. This state demonstrates an entry action, which in this case initializes the internal explosion counter to 0. The animation happens in the time tick event, which is handled similarly as in the flying state. First, the position of the explosion is advanced by one step, but here it means to subtract the game speed to keep the explosion scrolling horizontally at the same pace as the tunnel walls. Also, the explosion counter is incremented. The transition then goes to the choice point, where the guard condition checks whether the explosion is still visible on the screen and whether the explosion counter is below the limit of 15. If this is the case, the missile generates the mutable object image event with parameters, just as it was done in the flying state. An interesting aspect of setting the event parameters is that the bitmap number BMP is calculated from the internal explosion counter to select the progressing stages of the explosion. Finally, the event is posted to the tunnel to render the chosen stage of explosion on the display. When all stages of the explosion have been shown, or the explosion scrolls off the screen, the state machine transitions back to the armed state, where the missile is ready to be fired again. So this was just one state machine in your game, but other state machines are similar. And the last really interesting concept I'd like to point out is the use of state hierarchy to capture common behavior. For example, the state machine of the mines demonstrates the concept. Specifically, the superstate used handles the event mine recycle, which then applies to all the substates, planted, exploding, as well as any other substates that you might add in the future. Please note that here the action on the mine recycle transition itself is empty. But there is an exit action in the used state, and this exit action performs the required cleanup. Alright, I could of course go into details of all the other state machines, but I hope that you already got the general idea of the state machine design process and the kind of services you need from the underlying active object framework. Let's now move on to coding. Well, traditionally, at this point you would manually code all the state machines, and this is of course still possible. In fact, I will show you how to do this in a minute. But first, I'd like to show you how to generate the code automatically, because it turns out that you've already done all the required work. All that's really left to do is to generate the state machine skeleton, on which to hang your action code that you already provided. This can be automated, and the QM tool can do it for you. Just like this. So let me now explain what has been generated and why. If you worked with other modeling and code generating tools before, you might be used to the traditional way of generating a header file and a source file for each class in the model. For example, the files generated for the class missile would be missile.h with the declaration of the class and missile.c with the definition of the class. Similarly, there would be two files for ship, table, the two mine classes, and even for each and every event class. This turns out to be quite limiting and inflexible because you often want to organize your code differently. And you almost always need to include some additional header files and other code from outside of the model. In the traditional approach, this requires a lot of configuration options to adjust the code generation to your specific needs. For these reasons, code generation in QM works differently, and actually turns the traditional model upside down. So QM specifically does not impose any file structure, directory names, or the contents of the generated files. Instead, in QM, directories and files are first-class model elements, so the design of the generated code, which is called the physical design, becomes an integral part of the modeling process, just like the logical design is. In other words, QM is a unique modeling tool that supports the physical design directly. For example, in your game model, the model element corresponding to the physical design is the directory named the dot. This means that it is the same directory that holds the model file, but you can choose any other relative path to the model file. For instance, /foo will generate the directory foo one level above your game.qm model file. The directory contains the files and possibly other nested directories. QM recognizes the type of the files by looking at the extension, but otherwise it does not impose any content of the files. Instead, you provide the content of each file, which QM then copies over to the file on disk in the specified directory. So it is completely trivial to put in your files all the include directories, comments, and anything you want. But the twist here is that you can also direct QM to generate specific parts of the code based on the model items of your choosing, with the granularity ranging from the whole packages and classes down to specific state machines, states, attributes, and operations. For example, the highlighted $declare directive will be replaced in the file on disk with a declaration of the specified model element, AO's missile in this case. Similarly, the $define directives will be replaced with the definitions of the specified model elements in the file on disk. So now you can go to the directory containing your model and open the generated file, such as missile.c, with your favorite editor. So here it is. First, you can see the comment generated by QM telling you that this file is not to be edited manually. But then you can recognize a snippet of your code copied laterally over. And here is the generated declaration of the missile class. Please note the class inheritance in C implemented with the member super of the type QActive, followed by the attributes added in the missile subclass. Also note the class operations with the me pointer as the first parameter. And here is the most interesting definition of the missile active object class, which includes the whole generated state machine code. So now let me quickly show you how the generated code traces back to your state machine design. For this, I'll review just one state, exploding, but all other states have very similar structure. To trace the state to code, I'll use the copy model link tool, which then allows me to paste the model link into the search box of my editor. The search then will locate the special traceability comment in the generated code. So here it is. The QP state machine implementation maps each state to a specific class member function with the usual class name prefix _ state name. The function takes the usual me pointer to the class instance and the constant event pointer e. The state entry action maps to the case statement labeled with the reserved signal qEntry_sig. This case executes then the entry action code that you've provided in the model. Next is the time tick transition, which maps to the case labeled with a time tick sign. This case first executes the action code associated with the transition segment up to the choice point. Next comes the first branch of the choice point with a guard. This one maps to the if statement that evaluates the guard condition. Inside the if branch, you can see the action code that you've attached to the branch of the choice segment in your state machine. The else branch maps to the else instruction in your code, where you can see the macro qtran with the parameter missile armed. This is how you code the transition to the state armed in this case. And finally, the default case specifies the hierarchical nesting of your state. The exploding state happens to not nest explicitly in any other state, so it nests in the implicit QHSM top state. The final return statement from the state handler function returns the status of processing back to the framework to let the framework know exactly what happened. At this point, I hope you would admit that the right state machine implementation strategy makes the coding quite straightforward and you could quite easily do it by hand. All you need to know is just a few boilerplate rules for coding various state machine elements, like states, exit entry actions, transitions, guards, and state nesting. So if you are allergic to modeling tools, or simply don't trust them yet, you could simply sketch your state machines with a pen on paper and then code them manually. But manual coding is still manual labor, with ample opportunities to introduce human errors while not really contributing anything creative. A big benefit of code generation, besides eliminating silly coding mistakes, is that it will give you a much better mileage out of your models. Code generation is the deciding factor that tips the balance of making modeling worthwhile. Otherwise, if you code manually, your models will quickly become outdated and abandoned. You'll thus lose the higher level of abstraction and the visual aspect of modeling. In the final segment of this presentation, let me outline the various options for executing your active objects. I will also show you a few other benefits of the active objects that go beyond the traditional RTOS. Regarding the execution of active objects, you can look at the main function of the application, which is located in the file main.c. The most important things happening here are starting all the active objects, and then passing the control to the framework by calling the qfrun function, which executes your active objects and typically does not return. It turns out that you can link your application statically with different implementations of the qActiveStart and qfrun functions depending on which QP port you will choose. For example, you can choose the QP port to the traditional RTOS, where the qActiveStart implementation starts the private RTOS thread for each active object, and the thread runs the event loop. I explained this option in my last year's presentation of the aforementioned little FreeAct active object framework. But this was just one of many options. For example, the ports to the kernels called QV, QK, and QXK, built into the QP framework, take advantage of the fact that active objects don't block. For instance, let's take a quick look at the preemptive but non-blocking QK kernel to execute active objects. Such kernels are known and widely used. Here, for example, is the OSSEC VDX operating system specification, which is an automotive standard. The specification describes extended tasks, which are the traditional tasks that can wait, meaning block, as well as basic tasks that still can preempt each other but cannot block. It turns out that the no need for blocking drastically simplifies the kernel and enables all basic tasks to use a single stack. The QP framework provides, among others, a port to such a preemptive, priority-based, but non-blocking kernel called QK. QK can execute only basic tasks, but it is still fully compatible with the rate monotonic scheduling, rate monotonic analysis, so it can guarantee hard real-time performance. At the same time, QK needs only a single stack for all active object tasks, and in terms of CPU efficiency, it will outperform any traditional blocking kernel. And the last port I'd like to mention is the QP port to Windows, because it opens up a possibility of developing big parts of your embedded code, including most of the graphical interface, on the desktop, and thus bypassing the target hardware bottleneck. So here I have a Visual Studio project for the game, which uses exactly the same C code that the actual embedded target. This is possible because the board dependencies have been properly abstracted and separated in the board support package, BSP. The unique aspect here is that the graphical user interface part of the port, called QWin, is based on the raw Win32 API, which provides direct binding to C. This is in contrast to other approaches where people use C# with .NET or Visual Basic, none of which binds to C as easily. Discussion of the details of building realistic prototypes with QP is outside the scope of this talk. But online you can find documentation, including a detailed application note, as well as example code, like your game here. In summary, I hope that this presentation has shown you that you indeed can apply modern embedded programming concepts of object-oriented programming, the active object design pattern, and hierarchical state machines in embedded C, even in very small projects. You had to carefully avoid any sharing of resources among active objects, but in exchange you didn't have to worry about concurrency hazards or mutual exclusion mechanisms. Also, I hope you noticed that the method naturally leads to an actual design, whereas your main design artifacts, the hierarchical state machines, can be easily implemented in C in a bidirectionally traceable way. When it comes to software modeling, it has gained a somewhat bad reputation of being too heavyweight and not pulling its own weight. But modeling can be also lightweight, code-centric and quote-unquote low ceremony. Finally, you learned that active objects can run in a variety of environments, including very efficient kernels as well as desktop operating systems. All this opens new possibilities compared to the traditional approaches.